Welcome to today's lecture on the nature of data as part of our exploration of statistical modeling. Understanding data is fundamental because it forms the basis of everything that we do in analytics and decision making. Data is all around us. It's the facts we gather from observations, experiments, and experiences. And it can take on many forms. It can take on forms like numbers, words, or images. To put it simply, data is like the raw materials for constructing a house. Without a strong foundation of accurate and reliable data, any analysis or model that we build is going to be at risk of failure. So in this class, we're going to discuss how data is collected, why its quality matters, and how it's transformed into meaningful information and knowledge that we use in the real world. Okay, so let's go ahead and begin, by breaking down what data truly is and why it's crucial to analysis. So think of data as raw ingredients, almost like in a recipe. Data is the building blocks from which we're going to create information and ultimately knowledge. Just like a chef is going to use high quality ingredients to make hopefully a delicious dish, an analyst has to make sure the data that they work with is accurate and clean, because this directly impacts the outcome of the analysis, directly. Data can come in many forms. It can be numbers, words, or even images that's collected through experiences, observations, experiments. For example, in the real world, think of data collected from weather sensors like temperature, wind, speed, or rainfall, which meteorologists would use to make weather forecasts. So by understanding that data, it's the most basic level of abstraction, we can appreciate how data serves as the foundation for decision making in business, all businesses, all verticals, healthcare, higher ed, sports, and beyond. High data quality and integrity are not just technical details, they're the backbone of reliable analytics. So let's explore how data flows and connects different parts of our world. So in this slide here, what we're trying to show is the life cycle of data, from its sources like social media, business processes, Internet of Things devices, to its uses in applications. So think of data like water in a city. It's going to flow from various sources, like rivers and reservoirs, into a central system for treatment, like data storage and validation, before it's delivered to homes and businesses, i.e. the end users and applications. For example, platforms like Instagram and LinkedIn, they generate massive amounts of data, which these companies have to then analyze to understand trends or to improve user experience. So to make sense of this flow, the key is analytics. It's testing, building, and validating data. It's to make sure that the data is trustworthy and useful. So without careful protection and processing, the quote water supply or the data could become polluted. And this would lead to unreliable decisions. So this interconnected system, it shows how data drives everything from business processes to personal applications, reinforcing its critical role in our digital ecosystem. So to ensure data is ready for analytics, we have to evaluate data using a range of metrics. And that's what's outlined right here. And these metrics are going to help assess the overall quality and usability of the data. The data source reliability is going to ensure that the data originates from a trustworthy and consistent source, minimizing errors. When we say data content accuracy, we're checking whether the data accurately reflects the real-world phenomenon that it represents. Data accessibility ensures the information is readily available when and where it's needed. And this is critical for timely decision making. We have security and privacy measures that protect sensitive data from unauthorized access. And this maintains both integrity and compliance with regulations. When we talk about data richness, it refers to the completeness of the data. making sure that the data includes all of the necessary variables for analysis. Consistency ensures that there are no contradictions and there's no mismatches within the data set. And we talk about currency or timeliness. It makes sure that the data is up to date. Granularity focuses on the level of detail in the data, and this can impact the depth of your analysis. And finally, there's validity and relevancy. And that confirms that the data is appropriate and aligned with the purpose of the analysis. For example, when you're preparing data, let's say for a marketing campaign, making sure that that data is accurate, timely, and relevant, it helps avoid targeting the wrong audience. And that could result in wasted resources like money. So these metrics are vital to delivering meaningful insights and reliable analytics. So this is a taxonomy of data, dividing the data into two main categories: structured data and unstructured data, or even semi-structured data. Structured data is well organized, and it typically resides in databases or spreadsheets. It includes numerical data, such as sales figures, and categorical data, like product types or customer demographics. Numerical data, it's further classified into interval and ratio types, while categorical data is divided into nominal and ordinal, depending upon whether the order of the value matters. On the other hand, we have unstructured data that lacks a predefined format, things like text, images, audio, video. And we also have semi-structured formats like XML and JSON. And they have some level of organization, but they're not as rigid as structured data. So, for instance, a business might track inventory and sales using structured data in a database while collecting customer reviews or social media posts as unstructured data. So recognizing these distinctions, it's crucial because the tool and the techniques for analyzing structured data, it differs significantly from those used for unstructured data. So this understanding enables us to make better decisions when we're preparing and we're processing data for analysis. Data pre-processing, it's both an art and it's a science, because it involves transforming raw data into a well-structured form that's suitable for analysis. The process includes several critical steps. Data consolidation combines data from multiple sources, making sure that it's integrated and consistent. Next, we have data cleaning, and data cleaning addresses issues like missing values and noise and duplicates so that we can improve the quality. And once the data is clean, data transformation is going to modify it by normalizing values, making sure that we have discretizing continuous data or creating new attributes to make it more suitable for analysis. Finally, we're going to have data reduction, which is going to simplify the data set by focusing on the most relevant information. And this is going to involve reducing the number of variables through dimensional reduction, or selecting key variables and balancing or stratifying samples to make sure that we have a good representation in the data. What's a good example? Let's say you're analyzing customer behavior. If you pre-process the data, it's going to make sure that you have clean, consolidated data from different sources. The different sources could maybe be web logs or transaction records, and that the analysis is going to focus only on meaningful patterns. So this entire process lays the foundation for accurate and efficient analytics, making sure that the final data is both manageable and insightful. Statistical modeling, it's a key component of business analytics. It's divided into three main areas. The three main areas are descriptive, predictive, and prescriptive analytics. Now, we say descriptive analytics. What we're doing is we're talking about focusing on summarizing historical data so that we can understand what happened in the past, right? Often using tools like OLAP, right? online analytical processing to analyze and present data trends. When we look at predictive, however, analytics, we're going to use statistical and machine learning models so that we can forecast future outcomes. Okay? So when we say predictive analytics, that's going to be forward-facing. And it's all going to be based on the data. So a business might use predictive analytics to anticipate customer demand in the upcoming quarter. Might use prescriptive analytics, the last one over here. It's going to go one step further by suggesting the best course of action based on the predictions, combining advanced models with optimization techniques. So underlying all these approaches, though, are going to be statistical methods, both descriptive, which is going to summarize data, and inferential, which is going to allow you to, descriptive and inferential is going to allow you to draw conclusions from the data. So descriptive describes the data, inferential is going to allow you to draw conclusions. And together these methods enable businesses to move from understanding the past to making informed decisions about the future, providing a foundation for strategic growth and innovation. Statistical modeling, it plays a foundational role in business analytics. And it does this by providing the mathematical techniques that are needed to analyze and interpret data. So at its core, statistics can be broken down into two branches: descriptive statistics and inferential statistics. Descriptive statistics, it focuses on summarizing and describing data as it is, such as calculating averages, medians, or visualizing data through charts and graphs. And this is often used in descriptive analytics to understand historical trends or patterns in a straightforward manner. On the other hand, if we look at inferential statistics, this is going to enable us to draw conclusions about a larger population based on sample data using techniques like hypothesis testing and confidence intervals. So for example, a company might use descriptive statistics to analyze last year's sales. Okay? So sales from last year. On the other hand, a company might use inferential statistics to predict future sales based on a sample of recent trends. Right? So we'll go from these trends in the data to predicting sales in the future. That's going to be effectively the difference between, there's future, all right, the difference between descriptive statistics and inferential statistics. So understanding these statistical tools is going to allow businesses to better describe, analyze, and make decisions based on data-driven insights. Descriptive statistics, it helps us summarize and understand data by focusing on measures of central tendency. Measures of central tendency. Okay, in other words, what that means is that it's going to focus on indicate the center or typical value in a data set. So there's three main measures. There's going to be the mean, okay? The mean, and the mean is the average, okay? It's calculated by adding all of the values, right? The sum of all of the values. And it's going to divide that by the number of observations, okay? Every time, right? That's going to give you your average. However, the problem with the mean is that the mean can be influenced by outliers, okay? The mean can be influenced by outliers, and that's a problem. The median, sometimes it's a problem. The median is the middle value when data is arranged in order, making it a better measure of central tendency when you deal with skewed data. Okay? And then lastly, the mode is going to be the most frequent observation in the data set. Okay, that's all the mode is. So for example, if you're analyzing salaries, the mean might be skewed by a few very high earners, while the median is going to give a clear picture of a typical salary. So understanding these measures is critical to summarizing data effectively and making informed decisions. Measures of dispersion help us understand how spread out the data is, complementing measures of central tendency by showing variability. So variance is the first one that we'll look at. And variance quantifies this spread by measuring the average squared difference between each data point and the mean. Right here, the average squared difference between each data point and the mean. And in this case, if we use the numbers 1, 2, 3, the mean is going to be 2. So how far off is each one of these numbers from 2? And this is the equation that we use to compute that. So in this case, our variance is going to be 0.667. Okay? Standard deviation is the next one that we're going to look at over here. And it's the square root of the variance. Okay? The square root of the variance right here. This is standard deviation. Okay? And it's going to give you a... It's going to be useful for understanding how data points cluster around the mean. Okay, so the standard deviation is the square root of the variance and provides a more intuitive measure of spread in the same units as the data. And this is especially useful for understanding how data points cluster around the mean, as seen in the normal distribution graphs, where approximately 68%. Right here. So standard deviation. Approximately 68% of the values fall within one standard deviation of the mean, assuming that the data is perfectly normalized. So standard error is something else. Standard error, it estimates the variability of a sample mean compared to the population mean, and it's useful in inferential statistics. So I just leave that, alone for right now. We can come back to that later if you like. Lastly, we have the mean absolute deviation, the MAD, and it measures the average absolute distance of every data point from the mean, and it offers a simpler way to assess the spread. So these metrics are essential for analyzing data distributions, and making accurate inferences, whether evaluating product quality or predicting market trends. Measures of dispersion provide insights into the spread and the variability of a data set, and quartiles are key concepts for summarizing this variability. So quartiles, they divide the data into 4 equal parts. Quartiles divide the data into 4 equal parts. Each quartile represents 25% of the data. Each quartile represents 25% of the data. So that moves us to a box and whisker plot, or a box plot. So a box plot is going to visually represent this spread. So the box and whisker plot is a versatile and informative tool for understanding data distribution. The box plot, it displays what we call the interquartile range, which is the range between the lower quartile, right here, Q1, the lower quartile, and the upper quartile. Okay, the upper quartile is going to be Q3, or right here. Okay, and all of this in between is the interquartile range. All of that in the middle between Q1 and Q3 is the interquartile range. So the line inside the box, it represents the median. Okay, that's the half of the data. Half of the data have values above that. Half of the data has values below that in that data set. That line right there represents the median. The whiskers extend to the smallest and largest values within 1.5 times the IQR. So, for instance, we're going to get this value, whatever this value is right here, and we're going to multiply that value by 1.5. And we're going to take that and we're going to extend the smallest and largest values within 1.5 times the IQR. So that's what that max comes in over here, and then we're going to do the converse on this side over here. Okay? So that's where that comes from. So a box plot comparing two variables can help us identify whether one data set has more variability or it contains more outliers. It's a simple but powerful visualization that helps summarize large data sets, making it easier to detect patterns, trends, and irregularities. Understanding the shape of a data distribution is really crucial for descriptive statistics because it reveals key patterns and tendencies. A histogram is one of the most effective tools for visualizing the frequency distribution of numerical data. It groups data into bins or intervals, and it displays the frequency of each interval as bars, providing an estimate of the probability distribution for a continuous variable. So, for example, a histogram of tree heights, okay, that is literally tree heights, not three heights, but tree, T-R-E-E heights, might show whether most trees are of average height or if the data is spread out. So that's what we're showing over here. Okay. Another measure to describe the shape of a distribution is its kurtosis. And kurtosis, what that does is it indicates the peakedness or the flatness of the distribution. A distribution with a positive kurtosis, like over here, has a really sharp peak and a long tail. Okay, sharp peak and a long tail. While a negative kurtosis is going to imply something flatter, a flatter shape with lighter tails. So, for instance, in financial data, high kurtosis could signal the presence of extreme values or outliers, such as unexpected market swings. And these tools help interpret the nature of data distributions, supporting better decision-making and deeper insights. Skewness is a measure of asymmetry in the data distribution. In a symmetrical distribution, the data is evenly distributed around the mean. And the mean, median, and the mode are all going to be identical. Okay. However, when a distribution is, so this right here means it is symmetrical. Okay. In other words, there's no skew right here. It's perfectly symmetrical. But when a distribution is positively skewed, then the tail extends to the right. It has a right tail, right? It's asymmetric, and it has a right tail. You see the right tail going all the way down there. Okay, so the tail extends to the right, indicating that the mean is greater than the median due to the presence of large values. Conversely, right, you can have a negative skew, right? A negative skew. Or you can have a left tail, which means that the mean is smaller than the median because there's many more smaller extreme values. For example, income data is often positively skewed because there's only a small percentage of individuals that earn significantly more than the majority. Skewness can be calculated in tools like Microsoft Excel, Power BI, Tableau, pen and paper. But anyway, understanding skewness, it helps identify potential biases or anomalies in the data, enabling them to make adjustments or interpret results more effectively in scenarios like forecasting or customer segmentation. Histograms, like I said, they're an effective way to visualize skewness in the data set because they display the distribution of the data values. In a symmetrical distribution, such as human heights, the histogram, it resembles a bell shape with most values clustered in the middle and tapering off. And it'll taper off evenly on both sides. That's what you see over here. It's the same thing that we looked at before, and it's pretty much, right, normalized. Okay. So things like human heights. Okay. On the other hand, you can look at positive skewness, and we said positive skewness means you have a right tail, and in this case we have a right tail. It's evident in data like house prices, where there's a few high values, the luxury homes. They're going to stretch the tail to the right, pulling the mean upwards. On the other hand, negative skewness, which you see over here, negative skewness, it can be observed in things like test scores, where there's a few low values that extend the tail to the left, pulling the mean, the average, down. So you have to get comfortable with these patterns because these patterns help us understand the underlying characteristics of the data. For instance, in business, positively skewed distributions, they often indicate outliers or they indicate opportunities, such as identifying high-value customers, while negatively skewed data might reveal challenges or anomalies. So recognizing skewness through histograms enables more accurate interpretation and modeling of real-world data. Histograms are an effective way to visualize skewness in the data set also because they display that distribution of data values in a symmetrical distribution. In a symmetrical distribution, we're always going to be good. And we can almost always very clearly see positive and negative distribution. So, like I said, in Excel, you can go to options, add-ins, and in add-ins, you actually have to click go. That's a gotcha. You actually have to click go right here. And once you click go, select the analysis pack, but I'd recommend that you select all of them. And then once you select data, you'll see data analysis, and from data analysis, then the data analysis tools will give you tools for descriptive statistics or regression or, all kinds of things. You can compute, a bunch of stuff over here. You almost always want labels in the first row. You almost always want whatever you analyze to show up in a new sheet. And then from there, it'll depend upon your use case. Okay, so you can see here I created a simple box plot. That's just because it's an effective way to visualize the distribution and variability of a data set. And Excel is going to give you some great built-in features for this, right? You go under charts. Under charts, right, you can see the option to create box and whisker plots. In this example, data for expense and demand, it's analyzed. Okay, so to create the box plot, first you just select your data set, then you choose the box and whisker chart type. And then the resulting plot is going to display key statistical information, the median, the interquartile range, the minimum, the max, the outliers, everything. Everything's right there. So box plots are very useful for comparing multiple data sets side by side, all right, as you can see here. So this chart is showing you the spread and central tendency of expense versus demand, helping to identify patterns or potential outliers at a glance. Regression modeling, that's a cornerstone of inferential statistics and is one of the most widely used techniques in analytics. It is employed to analyze and understand the relationship between variables, specifically between one or more explanatory or independent variables, and a response, or a dependent variable. So this method, it provides a mathematical framework for quantifying how changes in the input variables affects the output variables. For example, a business might use regression to examine how factors like advertising spend, pricing, and market conditions, how they all influence sales revenue. Regression modeling, it serves two primary purposes: hypothesis testing and forecasting. In hypothesis testing, regression helps determine whether the relationship between variables is statistically significant, providing explanations for observed patterns and guiding decision making. For instance, a company could use regression to assess if customer satisfaction scores have a measurable impact on repeat purchases. In forecasting, regression models use historical data to make predictions about future outcomes, such as estimating next quarter's sales based on past trends and external factors. Regression's versatility extends to various domains: finance, healthcare, social sciences, where it's used to predict stock prices, patient outcomes, social trends. So its ability to uncover relationships and make predictions makes regression an essential tool for any data-driven approach to problem solving. So we can also look at, that's regression. Okay, so regression is just a fundamental technique in statistics. It builds on the concept of correlation, but it goes a bit further in understanding and predicting relationships. Correlation is measuring the strength and direction of a relationship between two variables. Regression not only quantifies this relationship, but also allows for predictions of the dependent variable based on changes in the independent variable. Regression comes in two plain forms: simple regression and multiple regression. Simple regression uses one input variable to explain or predict the output, while multiple regression, it incorporates two or more independent variables. For example, simple regression might analyze how advertising spend influences sale, while multiple regression could include factors like product price and seasonal trends. So to develop a linear regression model, analysts often begin with a simple scatter plot, which just visualizes the data and identifies potential linear relationships. The next step is applying the ordinary least squared method, OLS, which fits a line to the data by minimizing the sum of the squared differences, i.e. the errors between the observed values and the predictions. Now, this approach makes sure that the best possible fit for the data takes place, making regression a powerful tool for both explanation and prediction in fields such as business, healthcare, and social sciences. So, this diagram here, it's showing you the foundation of regression modeling, specifically linear regression, which examines the relationship between an explanatory variable, okay, which is the independent variable, and a response variable, the dependent variable. The regression line that's shown here, it represents the best fit line that minimizes the sum of the squared residuals, the differences between the observed values and the predicted values on that line. Okay, so the equation for this line is y equals mx plus b. I can go further, but just understand that we have our intercept there. We have the slope. This is pretty standard. So regression modeling involves establishing a mathematical relationship between an input variable and an output variable. In simple linear regression, like I said, that relationship, it's represented by the equation y equals mx plus b. Okay, that's what this is right here. Multiple linear regression, it means that we have multiple features that are playing a part in the prediction. So we're going to have our intercept here. This is multiple regression. And then it's going to be the feature value times some coefficient. Then another feature value times another coefficient. And all of this is essentially the dot product is all this is right here. That's all linear regression is. Add all of them up and you get your prediction there. Okay. So multiple linear regression allows for the modeling of more complex relationships, such as predicting house prices based on size, location, number of bedrooms. So those beta coefficients, though, they're all critical. Okay, they're all critical in interpreting the model. Their sign, whether they're positive or negative. This. Right? These signs here, whether they're positive or negative, indicates the direction of the relationship. How large they are indicates the magnitude, right? The strength of their effect. So regression modeling provides a robust framework for understanding and predicting real-world phenomenon across various fields, including economics, healthcare, engineering. So developing a regression model involves a structured process to ensure the model accurately represents the relationship between variables and can be used effectively for prediction or explanation. The process starts with data assessment, where scatter plots and correlation analysis are used to understand the relationships between variables. Next is going to be model fitting, where the data is transformed if necessary, and parameters such as beta coefficients are established. Now, once the model is built, model assessment is performed to test its assumptions and evaluate how well it fits the data. The effectiveness of the model is determined using metrics like R-squared, which measures the proportion of variance in the dependent variable explained by the independent variables. In R-squared, values close to 1 indicates a good fit. Now, p-values are used to test the null hypothesis. Lower values, values closer to 0, indicate statistically significant relationships. So, for prediction problems, error measures such as the mean squared error, mean absolute deviation, and root mean squared error, they help evaluate accuracy with lower values indicating better performance. And the final step is deployment, where the model is applied either for one-time use or recurrent use, depending upon the problem. So this structured approach ensures that the model is both statistically valid and practically useful. So logistic regression modeling, it's widely used, and it's a widely used statistical method, and it's designed for classification problems. So unlike linear regression, which predicts a continuous numeric outcome, logistic regression, it predicts a categorical outcome, often binary, like yes or no, success or failure. It employs supervised learning, and it was developed in the 1940s to model probabilities. The target variable in logistic regression is typically expressed as a binomial response, with the model output representing the probability of a particular class. For example, in the data set that you see right here, logistic regression could be used to classify wine types based on their chemical composition properties, such as alcohol content, acidity, phenol levels. So this method, it calculates the probability of a wine belonging to a specific category and assigns it to the most likely class. So the output probabilities are mapped using the logistic function, which constrains predictions between 0 and 1, making it suitable for binary classification. Logistic regression, it's a highly interpretable and widely used in fields like healthcare to kind of predict disease presence and marketing, customer churn prediction. Its simplicity and effectiveness makes it a powerful tool for understanding and predicting categorical outcomes. So, what did we cover? We explored the foundations of statistical modeling and its applications in data analysis. We began by examining the nature of data, understanding its type, whether it's structured or unstructured or semi-structured. We covered the importance of data quality metrics such as reliability, accuracy, and timeliness in ensuring analytical readiness. We then discussed descriptive statistics, focusing on measures of central tendency, mean, median, mode, and dispersion, variance, standard deviation, and skewness, so that we can summarize and interpret data distributions. So visual tools like histograms and box plots, those were introduced to reveal patterns and variability in data sets. And then next we jumped into regression modeling, which is a key to inferential statistics. It's a key tool in inferential statistics to help us understand relationships between variables. Simple and multiple linear regression were introduced along with key concepts like beta coefficient, scatter plots, ordinary least squared methods, things like that. We explored the process of building regression models, including data assessments, model fitting, and evaluations using metrics like R-squared and p-values and error measures like mean squared error, mean absolute error, root mean squared error, things like that. Logistic regression was also highlighted as a classification tool, distinguishing it from linear regression. Logistic regression is able to handle categorical outcomes, true, false, yes, no, big, small, horse, cow, cat, dog, whatever, with applications ranging from like customer segmentation to medical diagnoses. So through these concepts and techniques, this lesson emphasizes the importance of statistical models in turning raw data into actionable insights. Whether for descriptive analysis, predictive, or classification, these tools, they form the backbone of data-driven decision-making across variable fields. My name is Dr. Lee. Thank you for making it this far to the end.